So first off, we have Professor Sethu Vijayakumar, who is the director of the Edinburgh Centre for Robotics, and he's going to be talking on robots that learn, the future of man, or the man of the future. Sethu's research topics include robotics, machine learning, motor control, and various aspects of computational neuroscience.
Thank you all, and thank you for coming. It's a pleasure to talk to an audience. It's a diverse audience, and it's not the audience I'm used to talking. So I hope I come across legibly. So let me just try and get the lighting right.
So can everyone hear? Because there's a mic up there if you want it.
I'm usually quite loud. So can everybody hear me?
Yeah.
Yeah. I think I'm happy to just go with that. The topic of today's talk I'm giving is robots that learn, the future of man, or man of the future. So it's actually the title has some connotations. One of the connotations is that are we going to have robots that would replace humans at various tasks? So some things like certain elements of autonomy, certain levels of working in an industrial setting, certain things in the domestic setting, or whether we're going to actually look at the future of man. In other words, are we going to look at robots that don't really take away human jobs, but actually combine and actually work together in cohesion with robots? So examples of with humans. Examples of that include things like exoskeletons, things where variable robots and the likes. So today I'm going to try and get through some of the research that we do here in Edinburgh, and also give you a broader perspective on the challenges of creating autonomous robots. So let me start by showing you two little clips. So BBC Bangles a Theory, I'm not sure how many of you watched that, but they came to our lab about a year and a half, about 2 years ago, and they shot two little clips. And the first one was these bunch of football playing robots. So, so these are examples of these robots. These are fully autonomous in the sense that you don't have a supercomputer sort of linked to it. It's communicating wireless, but a very small bandwidth. But everything else, there's a computing on board. There is touch sensors and laser rangefinders, as well as infrared sensors. It's got cameras and it's got microphones for auditory sensing. So here the challenge is to get these robots to localize itself, recognize objects, figure out where it is with respect to the world, and actually, in this case, shoot a ball towards the right goal. So that's not very obvious all the time. So it sometimes sees a goal and it says, if it's not localized properly, it may shoot in the opposite direction. So if you notice that actually in the new rules, both the goalposts have to be exactly the same color. So there was a second clip where they actually showed a Connect 4 playing robot. There's another robot that we have in our lab. Apologies for the quality between. But this is a robot arm which is able to play a game of Connect 4 against you. And more often than not, it actually beats you. So it's pretty robust in its game playing, and so you get to go first, and it's a very fair system. But so the best you can actually do is get a draw. So that was then maybe, so in terms of the order of introduction, it said, look at these poor sort of football playing robots struggling on its feet, and look at the smart robot which can beat a human at a game of Connect 4. So if we ask the general public versus if you ask roboticists, which of the two is the smarter robot, you sometimes get very disparate answers. And there are reasons for it, and the reason is that when we're doing research in robotics, we think about smartness in robots as something where you have to incorporate things like autonomy, things like autonomous decision making, and more importantly, it needs to adapt to the changing world and react to unseen scenarios. So my 6-year-old can actually beat this robot even if she doesn't know how to play a game of Connect 4 by preventing the robot from putting the coin into the right slot, or moving the slot a bit, right? So at the moment, this robot doesn't have the ability to adapt to a changing world or react to unseen scenarios. And in some sense, what is missing is the ability to learn and adapt. And that is what I'm going to focus on today. So how we try, through our various elements for research, trying to put some element of learning, ability, and adaptation into our robotic platforms. So, in spite of this, there are already very good examples of robots which are already doing quite well in the everyday world. So, these days, there's lots of quadrotors in the news for good and bad purposes. So you've got privacy concerns, but it's getting there. It's really getting to a stage where we can do lots of stuff, including getting your next package from Amazon from one of these flying ones. Automated driving has matured to an extent that we've got large cities, towns, even states in the US where they've passed legislation to allow automated cars to drive on highways. There's obviously flexible manufacturing, prosthetics. You'll see some examples of that today. So we'll show you some live demos of that. And things like surgery and rehabilitation. So this is an area that we work on a lot in terms of lower limb rehabilitation, as well as there's some work in companion robots. So robots like Paro from Japan, which is about being empathetic with its users. So I think it's up to people to judge how empathetic things are. But so these are domains where robots are already making a difference. So what I want to get across today is some elements of what it takes to program a robot and make it adaptive, make it intelligent, make it possess some level of what sometimes people call artificial intelligence. So a quick schematic diagram of a sensory motor control would look like this. You have some plan, you pass it through a controller, it generates some motor commands, then you have a bunch of sensory apparatus which senses the state of the world, and then you go around in a loop in a sort of what we call sort of PID control loop in control theory. And funnily enough, a lot of the things that humans solve at the level of doing everyday tasks like reaching for a cup or just walking, it involves solving some of the problems that robots have to solve doing this. So what I'm going to look at is these kind of 4 areas: sensing, planning, moving, and representation. And I'll give you little examples of that. And again, in my abstract, I had sort of written that one of the things that's changing robotics from what was 10 years ago is the fact that a lot of machine learning approaches, so data-driven machine learning approaches, have actually been applied to the field of robotics, and that has created a huge amount of success. And I'll give you examples of that while I go through this. So there are interesting machine learning challenges in each of these domains, and things like incomplete state information, planning under redundancy, incomplete knowledge of the cost function that you're approximating. Especially in moving, we've got more and more complex robots, so it's hard to model them analytically, so you need data-driven methods to model them, and obviously representing your problem in the right space. Everybody here probably knows much more about me about this concept of working in the right space. So let me start by looking at this problem of getting robots to move and how machine learning or data-driven techniques are able to deal with this. So essentially what I'm looking at is what's inside this yellow box. So traditionally, if you control a robot in an industrial setting or in a sort of, if you're doing feedback control, then this is what a traditional feedback controller would look like. You have some desired trajectory, you look at where it is going and you sort of do some sensory feedback, and again, if you're trying to do that using some low gain PD control, you will get a behavior like this, where by the time the robot gets to where it's supposed to be, the actual target's moved away. Of course, you can crank up the gains very, very high. That makes the robots heavily dangerous because you're trying to be in its path, it will really rip your arm off. So that's a trade-off. You either work with soft compliant robots and with low gains, in which case there's a problem like this, or you have relatively low gains. So, but humans are very good at dealing with both accuracy as well as compliance. So how do we do that? So one hint is that we actually we do not just use feedback as a mechanism, but we actually predict ahead the consequences of your action. If you can predict ahead the consequences of your action, then you can plan very well, and you can basically reduce the need for providing high gain feedback. So that's what I mean by there's a little feed-forward controller that helps you do this. So if you now think about what is inside a feed-forward controller, both in humans and in robots, there's some interesting analogies. There's a huge literature in terms of what is inside a feed-forward or a feedback controller. But if you think about a typical predictive model of a robot, let me show you, flash up a little equation, but this is just to show you that if I've got 2 degree of freedom robot, an artificial 2 degree of freedom robot, equation of motion would look already fairly complicated. So torque at one joint can be written by a bunch of these equations, torque at the second joint is written by a bunch of these equations, and in theory, we can use this set of equations to control this 2 degree of freedom robot. And that's what would go inside a feed-forward controller, because then you can predict without actually having to apply forces what would happen. Now, if I scale this to a robot which is just 7 degrees of freedom, so just an arm, it's going to look horribly complicated. So the complexity of the analytical dynamics grows pretty quickly. So there are techniques to deal with this. So traditionally, you apply Newtonian dynamics to deal with this, and people have done this. But the point is, as the complexity increases, you get the number of joints increase, the complexity of what you're trying to learn or what you're trying to encode as a forward predictive model becomes more and more complicated. And that's the reason why sometimes people do low gain feedback control. In other words, you just try to react to errors, and that's where this early problem comes back. So what's an alternative way of doing it? An alternative way of doing it is learning from what we call motor babbling. In other words, you get the robot to explore parts of the space that you're interested in, collect the data, and then use the techniques from machine learning, data-driven model building to actually drive this. So we can either do some sort of random motion or sort of kinesthetic demonstration of some dynamic targets and make this happen in real time. So that's a significant part of my research early on when I was doing my PhD, was focused on how can we get real-time learning on high-dimensional robots to work. And that was very unique sort of 5-10 years ago, and now people use those kind of algorithms that we've worked on a regular basis. So it's become commonplace to apply machine learning techniques to robot control. So let me give you a little quick snapshot of how it works. So basic idea is do some nonlinear regression. Nonlinear regression means I'm learning a function which maps between my current state and the desired states to torques at every joint. So that's the bottom line. And you do this in a data-driven fashion. I won't go into the details of this, but effectively you fit some nonlinear function to some, you fit some local linear function to some nonlinear function, and you do this in an incremental online fashion. So we've worked on this algorithmic elements for a while now. But the trick is to make this happen and work is to really look at the data that's generated when humans move. So we do not cover the entire part of the workspace when we move. We have some very idiosyncratic movements. We move in a particular manifolds, either because we are all interested in minimizing some form of energy or some form of smoothness criterion or some form of elegance, maybe. So although if you record movements from 10 different people doing similar things, you will find interesting similarities in the way people move. And that is what you can exploit by looking at low-dimensional representations. And we collected some data on people doing everyday tasks, and we found that there are indeed these interesting low-dimensional representations. And if you can exploit that, we can live and work with these high-dimensional robotic platforms. And that's exactly what we did. This is a little schematic diagram of the algorithm that we used. And those of you who know the cerebellum would perhaps look at this and say, wow, that looks like a kind of a slice through your cerebellum. So it's not a coincidence that I've drawn this like that, because indeed cerebellum is known as a seat for motor control learning adaptation. So deficiencies in there can result in poor learning of new models of motor control. So let's see this algorithm in action. So what you'll see on the left here is the robot doing motor babbling, and effectively it's doing some random sinusoidal forces at every joint while doing some high gain PD control. So effectively the robot is recording the forces that it's applied at every joint and the consequence of its action. So it's a full state information it's recording. So torques, positions, velocities, accelerations at every joint. So at the end, we feed this data into this learning process that I just talked about, and we acquire the internal dynamics, or what we call the forward model of this robot using this data-driven technique. So once we've done that, then you know that if you've done it sufficiently well, with sufficiently rich data, then you know that you can move or command the tip of this robot to move wherever you want it to, because you've got sufficient control over, or you can predict what forces you need to apply for this robot to move. Then on top of that, you can do some interesting things like learning to balance this pole. And this is again a function that you learn on top of this. So this is learning to, in this case, learning a tool function which says that the only thing it's given is keep these two balls vertical, so you don't need to do anything else. And the robot basically explores the space of actions that it can make. Now it knows exactly how to move its arms. So it explores that space, in this case, 2D plane, and looks at the consequence of its action and eventually learns an appropriate response for every part of the state space. So that's good. I mean, to be frank, once it had learned the dynamics, this inverse cut pole problem could be solved analytically as well. It's a classical problem in control. It's called an inverse cut pole, so you can write down analytical equations. But what is really nice about this framework is if something changes, say I remove the tennis ball from top of this pole and change the dynamics of this pole, then you don't have to rewrite a set of equations to actually compute a new equation of dynamics. What I can do is I can apply the old commands and look at how it reacts, and obviously it's going to fail a few times, but all the time, because it's incrementally adding this data into the database and learning, you can very quickly see it adapts and change, and now it's modified its internal model of this tool use to improve things. So to be frank, this is work that we've done sort of 5, 10, close to 10 years ago now, and it's still quite a nice illustration of how adaptation can be done in a data-driven fashion. And I mentioned there was a question of whether humans do this as well, and indeed there's very strong evidence that we do indeed internalize some of the some of the changes in your system. So again, most of you have probably seen this experiment already, but I'll just repeat it. So this is a manipulative experiment, a classic manipulative experiment, where the top view of a person sitting with a manipulatum and reaching for a target. If you want to go from point A to point B, you can do that even if you close eyes. I'm able to do that very easily. And then if I have this robot here pushing you to the right all the time while I'm trying to reach for the target, if it pushes you to the right, then what happens when you try to reach for the target is you get deflected to the right. You give a person a few trials with the system. Eventually, you can compensate for this and improve your model to get straighter. And then, if you take this force off from the system, what happens? You overcompensate in the other direction. So that is real evidence saying that we are not correcting for things on a sort of trial-by-trial basis. We're not just compensating for errors. We've actually internalized something here, which is a systematic force which pushes you to the right. I've internalized that, and when I now take this off, my belief about the internal model is wrong again, because I've internalized this force which pushes you to the right. So that's why I overcompensate in the other direction. So this is evidence that indeed we do internalize systematic dynamics changes, and it's a good way of doing this for reacting very well and in a good fashion. And the same story when you sort of start it off again. Okay, so that was about learning to move and adaptation for learning to move. Next, I want to show you some fun videos of work that we've been doing and other groups have been doing in trying to sense. So again, making sense of the world is very important, and trying to sense the world under significant noise, under multimodality, under unknown causal structure is really hard. So sensing and imitation is something I want to show you a few examples of research that we've been doing in this domain, and effectively looking at this part of the control diagram. Okay, so this is work from collaborators at DLR in Germany. So this is the German aerospace guys, and this is Justin, which is a robot which is...
Catching a thrown ball with the hand is not easy. A tight interplay of fast perception, a good catching strategy, body control and dexterity is needed. Stereo cameras track the balls, and an IMU measures the 6D head pose to account for not completely cancelable vibrations introduced to the robot's lightweight structure due to the rapid catch motions. Based on the continuously improving trajectory predictions, a real-time path planner running on an external cluster repeatedly decides where, when, and in which configuration to kinematically optimal catch the ball. The resulting joint paths are executed by the arms, torso, and mobile platform. The head joints are controlled to keep the balls in the camera's field of view. The hand closes at the planned catch time. For easy user interaction, an iPad-based interface is provided. The system robustly reaches the necessary precision of 2 centimeters in space and 5 milliseconds in time, leading to a catch rate of over 80%. Despite the challenges of vibrations, elasticities, distributed sensor, actuator, and computing resources, this is achieved by combining the right sensors, intelligently taking the different precisions of the kinematic subchains into account, and thoroughly handling all timings in the sub-millisecond range in the software.
Okay, so that's an example of using really fast sensing, prediction, and to some extent learning of the forward kinematics to actually catch things. But you've seen here that most of these things, the objects that you're trying to catch were completely visible. So obviously the next challenge is what happens. Humans are very good at reaching things that are partially occluded. So one of the things that we've worked on as well is dealing with occlusion, dealing with again, using data-driven techniques to, first of all, build the model of how things move around, the kind of occlusions that can occur, and in this case, it's a real-time object pose recognition and tracking with visual servoing. And you will notice here that in the first instance, there's lots of significant occlusion. So this is, we've used a data-driven technique to learn the model of things that we care about. So even though the bottle is occluded, it still tracks the actual position. Even when it is really close to the camera, where it loses most of the object, it can still track the object position. And you can see that. So again, this you can see if you come to our lab on the first floor in Edinburgh in informatics. You can actually see this in action. And this is a big improvement in real-time tracking of occluded objects and using, again, data-driven techniques. So you'll notice here the camera is still. The next bit, you'll actually see that the camera itself starts moving. So that's the other bit. If you've got a robot, the body of the robot itself is typically moving around. So tracking under occlusion and under significant motion of the camera itself is a big challenge, and that's what we've been trying to look at. And again, sort of data-driven techniques are behind making this happen. And you can sort of think about various scenarios where you've got fast motion of the camera and you're trying to localize things. So that was about getting the sensing right. So one's with fully observable scenarios, another one where you've got significant occlusion. So now, once you've got the sensing sorted, so one of the things you could do is to now get robots like these to move by sensing a person move and mimicking that motion and putting this motion onto the robot. So in other words, you can get robots to prime its movement by person showing it. So for example, if you go to a tennis coaching class, you would actually look at the coach and actually make that, try and transfer that motion. So there are various challenges in doing this. Obviously the kinematics is a big challenge. A humanoid, however much you try to make a robot like a human, the degrees of freedom, the joints, the kinematics are very different, and dynamics is another big problem on top of that. So we've done significant work on making this real-time transfer happen. So what I'm going to show you first is a quick demo of, let me see if I can get the light back on. Okay, so I'm going to show you two things. So one is the demo of this robot here, and this one as well. Okay, so the first bit here is we're just going to get, so this is it's a 19 degree of freedom robot that's constructed by regular sort of servo motors. But what we've done is taken the motion of a person doing certain actions, and then we've actually literally mapped that motion per joint to the robot, and it's completely open loop, which means that it's got some gyro sensors and IMU sensors which keeps balance, but if I push it significantly, it will not recover from it. So I'm just going to go ahead and play it. So it's just playing back a movement which I've recorded from a person and mimicked this back. There's always a tricky bit here. So this is an example of a completely open loop transfer of human movements. So basically, this is one way of transferring motion. So instead of programming every joint individually and trying to coordinate this behavior, what we can do is get a person to show a particular behavior and then essentially deal with the kinematic correspondence problem. So the second bit is more about trying to get more reactive behaviors into it. So this robot here, it can play back motion that's been pre-recorded. So I'm going to first show you, hopefully, a motion that we've pre-recorded. So this is pretty impressive in terms of its balance, but again, it's a playback of the same movement. Okay. So that was the robot playing back a particular motion. But now, if again, this was completely open loop, meaning that there was no feedback. But I can show you the first level of feedback that it can do. It can change its behavior. For example, if I touch the sensor here, it's reacting to a particular signal which I've programmed it. So in other words, it is able to take external input and change its behavior. So this is one trivial way of changing its behavior. There's a slightly more sophisticated way of changing its behavior, which is, now I can press this button and I can lay it down, and hopefully it'll try and get up on its own. Okay. So that was good. I could do the same thing. I could press the same button. Okay, so it's the same trigger. But now I'm going to get him to, I'm just going to lie him down this way. So here, this is an example of the same behavior, the same trigger. Okay. So the same trigger resulting in two different behaviors based on the current circumstance, whether it's got a gyro sensor which tells it's the state of the system, which says I'm either face down or the other way around, and based on that you can see how it reacts in a slightly more intelligent way than the naive, here's a button, that's what it should do, kind of automating kind of way. Then finally, I'm not sure if this is going to work, but we'll give it a shot. So the lighting condition is always a challenge. But what we'll try and do is to get the robot to track and follow this ball. So, let me have a look. It works. Okay, so this is the kicking. So this is the basic kicking behavior that the robot's supposed to do. But now we'll try and get him to actually reach for the ball and do the same thing. I can move it around, and you'll see that it reacts to that. It's quite slippy, the surface, so I think it may or may not succeed kicking the ball. It's a bit confused as well. Okay, so it's not going to make it because it's trying to hit it. Okay, so we'll give it one more shot. So let me try to face it the other way around if the lighting conditions are better. Okay. Oh dear. Okay. No? Try. Oh, I'm hitting the wrong button. Sorry. Okay. Let's try that. There's something wrong, okay. Okay, so one last try. Try. So I think let's try one thing. I think this thing's a bit slippy. So it's put off by its. Let's see if that works. Was lost. Could be. One last try. Usually works. Yeah, that should be okay now. Yeah, it's better. Okay, I think we're going to give up. But yeah, at least you can see it react to. We've still got a long way to go. So that's why they're funding my research. We solved the problem. Okay.
Warning. This joint required re-pitch 73 degrees, look-and-you pitch 74 degrees, you pitch 79 degrees, rank play pitch 81 degrees, bye-bye.
Okay, good. So that was a bit of fun. Okay, so we've taken this whole concept and closed the loop, and here you will see a little video of two of my students. Suited up and we're able to capture their motion in real time, and we can get an avatar that you can see in real time actually mimic their character, and again completing the loop we can get a robot to mimic them in real time. So I'll show you
the latest motion capture facility. And, so for example, you can get people to actually perform the kind of motion that you want the robots to do.
Okay, and here's an example of the robot sort of directly cutting the middleman, if you may, sort of mimicking the motion. And as you can see, because of the morphological differences, when one step gets translated to multiple steps for them to actually move. And again, this is real-time motion capture, transference and correspondence with kinematic filters and dynamic filters, and then onto the robot in real time. So these are examples of how we can transfer motion across the robot. And this notion of using sensing and using teleoperation, in this case you saw a person teleoperate the whole body motion of the robot, is applied in many fields, including in this case the Da Vinci machine, which is from Intuitive Surgicals, and this is a demonstration of this sort of invasive surgery machine, in this case peeling a grape. So it's not really, so don't worry if you're queasy. So here obviously the main idea is you have a person teleoperating it, but the person itself may suffer from tremor and inaccuracies, so the robot takes out those elements and indeed this is under feedback, but you have fine precision monitoring of things, so in this case you're sort of peeling a grape while under teleoperation, and this is you can do fine precision operations. Again, this is kind of marrying the best of both worlds. It's marrying the contextual decision-making capabilities of humans and the precision and accuracy and repeatability of robotic platforms in sort of an interesting way. And here you can see the person actually teleoperating the device with a little phantom. Again, you need a bit of practice for doing that. So that was on sort of sensing and imitation side of things. I want to look at planning elements next. So planning has been done in various ways in robotics. So I'm not going to talk about the traditional planning. So for example, if you've got a full-bodied humanoid or a mobile robot, planning typically means trying to build a path either around the environment or for a humanoid to grab things, wrap things around, that kind of stuff. So that's traditional planning. So I'm not going to talk about that kind of planning, but I'm going to talk about planning in a slightly different scenario. I'm going to talk about planning in the scenario of working with variable stiffness, variable damping. So let me skip this, and I'll just show you straight away what I mean by that. So here's a little example, a toy example of a little 1 degree of freedom joint that we built at our lab, and it's got 2 springs, and it can move the arm by moving either of the 2 springs. It's a redundant joint, so it can move 1 spring. If you move 1 spring to the right, it'll push you to the right, and this other one pushes you to the left, but you could also simultaneously move it. And this is connected through an EMG sensor, so sensors which sense the activity of your muscles through some circuitry to correspond to. So if I actuate this muscle, this spring moves. If I actuate this muscle, this spring moves. And you'll see that I can do that, and I can make the single joint move left or right by doing this. But I can also have an alternate strategy. I could move this while co-contracting. I could do that while I'm very stiff with my legs. So this is an example of a co-contraction. So I could make the same movement while I'm co-contracting. And the difference between making a movement while co-contracting and not is if I have some disturbance, then when I'm co-contracted, the disturbance rejection happens automatically. So without any additional control, at the expense of additional energy. Obviously, when you co-contract, you're spending more energy in making this movement, but you're changing the dynamics of the system to reject disturbance. And the idea is, can we optimize this trade-off between expending more energy and optimizing the stiffness characteristics of a plant to optimize the thing that you want or care about? So that's what we did under the planning scenario. And why we care about such kind of planning is because, for example, we work with a collaborator in Japan on these kind of exoskeletons. So these are the Cyberdyne in the University of Tsukuba. And when you talk about exoskeletons, then you do care about compliance. So for example, this is the traditional very stiff, if I push against it, it'll push back kind of scenario. On the other hand, this is an example of a robot which has got low stiffness, high compliance. In other words, it's trying to make a desired movement while so it's trying to follow the 8, but at the same time it gives in when you push against it. So this kind of compliance and safety is paramount for exoskeletons, because you don't want the robot actually driving you, in fact. So you need to have some biosignals which make it helps you do stuff, but at the same time be compliant. So again, so in the interest of time, I'm going to skip through some of the details, but I'll show you some work that we've done with compliant robots. So we've worked with, again, the DLR, the German aerospace guys, to build a robot like that, and you will see some compliant robots again if you come down to our lab on the first floor of the informatics building. And we basically used an optimization framework, again, machine learning techniques, to actually optimize for this movement. So I'm not sure if you're interested in this kind of stuff, but let me go through this. So essentially what you do is you do optimal feedback control, which means that if I'm given some characterization of the system based on some equations of motion, and if I have some cost function that I'm trying to optimize, and this cost function may be a combination of some final cost like accuracy and some running cost like energy, and then I use an optimization technique to optimize for this, to maximize this cost or minimize this energy given this dynamics of the system. So we do this now in the space of variable impedance. So not just in terms of the planning, but in terms of the impedance characteristics. So if you put it in pictures, it looks something like this. So you have this traditional way of controlling things. You have some analytical dynamics and some cost function. You feed it to a controller and you execute a law, you make the movement. Now instead of the analytical dynamics, what we do is we replace the analytical dynamics with this learning model. In other words, we have something which feeds the data back, and you do this internal model learning that we talked about earlier. And the advantage of that is that you can, first of all, learn from data. And this is the spirit that I talked about in the first part of the talk. But you can also deal with perturbations and deal with changes to your model. If I've got a heavy load that I carry, then I can adapt this model. Plus, I can learn the uncertainty. I can learn the underlying uncertainty in the model. And if I learn the underlying uncertainty in the model, that results in much more intuitive, finer control. An analogy is, in reinforcement learning, I typically give the analogy that if you have to go from point A to point B, and I have a bridge which is really narrow, and if I fall off the bridge, I die. Or if I have to take a distance which is sort of twice the distance to get to point B. Now, what is the trade-off? So I do have to take stochasticity of my body and my system into account. So if I'm driving a unicycle, which is highly unstable, I would probably take the longer route. But if I'm pretty good at walking pretty steadily, I might take the narrow bridge and cross at a lower cost. So that element of taking the dynamics into account and the uncertainty into account is very relevant for this kind of work. And what we've done is we've taken this approach, and let me try and show you a nice little video of a variable impedance robot that we've actually built in the lab. And this is a 2 degree of freedom robot, and it's got every joint has the ability to vary its stiffness. So, yeah, it's basically a kind of a baseball throwing robot, but it's effectively able to pump energy into the system and induce more energy than what an individual motor can. And the idea is that by adjusting the stiffness, just like we do when we do a baseball throw or when we pump energy into a system, by adjusting the stiffness, we are able to maximize the release velocity and throw very fast. So this is an example of optimizing, planning the optimization under the stiffness modulation characteristics. So again, I'm going to skip some of these things and let's jump to apply. So we also applied this to this really complicated variable impedance arm, very high degree of freedom, and this is a slow-mo of this arm throwing. And you can see it's very different from a stiff robot throwing. It's very similar to what a compliant human arm would throw, and it's got it sort of releases backward swing and sort of releases when it sort of swings backwards. It adjusts its compliance in its joints to achieve, in this case, a higher throwing distance, for example. So it's funny where this has taken us. So we've taken this and applied it to everything from, in this case, we applied it to some variable impedance actuation to generate higher green energy. This is a Pelamis snake, and we're now building a 1 in 50 scale model of adjusting the impedance during the motion of the snake to extract more energy. So this is completely opposite of stability. We want to induce instability into the system to maximize output. Right? So this is something that we've been working on. We've worked on some very a brachiating robot, and this is an example of a simulation of optimization using the natural dynamics. So exploiting the natural dynamics and changing the impedance to minimize energy consumption during brachiation. So again, apologize for the quality of the video, but this you can see now, it's almost like an ape swinging, and the idea is you can optimize this. I have a video of this working in hardware as well, but it doesn't play properly, so I'm going to skip that. So where are we going with these kind of things? So this variable impedance stuff. One of the first application domains we're looking at is, besides the sort of wave energy and sort of robotics, is in the area of prosthetics. So here's an example of prosthetic work. This is not from our lab. This is from the University of Vanderbilt. And this is an example of a prosthetic leg, an active prosthetic leg, which can change its behavior. So this is now adjusting the phase based on the phase on the good leg. And initially, it takes a while for the person to kind of get used to during the walking gait, but eventually they get the hang and they start walking much more naturally. But what's missing here is that the stiffness at which the robot leg or the prosthetic leg is connected to a person's limb is pretty fixed. So whether he's walking on solid ground like this or on a mushy ground, on grass, we would have the same impedance. What we're trying to do is to try and take this approach of being able to modulate the impedance and build new kinds of systems which are able to adapt and change these things. So again, if you come to a lab, you'll see a little device that's built completely in-house. So it's certainly not ready for the market. It's got tons of wires sticking around and all this kind of mess around it. But it's got the claim to fame that it's the first robot in this world which is able to change both the impedance, both the stiffness and the damping at every joint independently. And we've got some first results on making this kind of bipedal walker walk on different terrain and able to adjust its stiffness based on whether we are stepping on hard ground or on soft thing. So again, the idea is to push this towards the prosthetic domain when this is ready. Okay, so last bit is working in the right space. So again, all of these things, when we talked about planning, talked about control, talked about representation. There's a saying in machine learning that you can have a really smart algorithm, but if you apply it on a space that is completely wrong, then that's no good. On the other hand, if you work in the right representation, the right space, and you define your problem very well, then pretty dumb algorithms can work pretty well. That is indeed our experience. And actually, some of the stuff that we work on, again, I won't go into the details of this, but we focus on representing the movement or representing the task that we care about in the right space, so that when we plan with algorithms, then the algorithms are able to exploit the fact that we have defined the problem very well. I'll give you an example. So here's an example of trying to get a robot to reach inside a box, and all it's supposed to do is to just stay inside the box. So typically in robotics, what people do is they will specify the forward kinematics of the robot, and they will specify a point in the center of the box, typically right at the bang in the center, and say reach for that, and if things move, then you sort of adapt, move its end effector accordingly. But when you say go inside the box, it doesn't mean be right in the center of the box. You can be a bit to the left or the right as long as it's inside the box. So that's what we do. So we try and look at using what we call interaction mesh as a way of representing the movement. So in this case, it uses this relational concept of looking at how, say in this case, how a robot, the end effector is relationally with respect to the entire box. So what you see here is when the space moves, the concept of what is in and out moves with it. So it's not metric anymore, it's a relational metric, relational concept. So that's why the robot doesn't move till it knows it's going to hit its edge, and then once it's near the edge, it starts moving. So this is the concept of working in the space of, in this case, interaction mesh, so that you can adapt the motion to novel situations. In this case, if you're thinking of reaching through a hole. So this concept of keeping a particular remapping versus replanning. So if things move, then the motion gets adapted automatically because of this relational concept rather than absolute concept. So that's the nice thing. And we've applied this concept to very many things, like in this case, we're thinking about how do we get a robot to wipe a surface, and this is in collaboration with the Honda Research Institute, and you've probably heard about the Asimo robot. So this is about giving many, many examples of a wiping motion and getting the robot, in this case, to generalize this concept of what it means to wipe, rather than having a metric notion of, go from point A to point B, and then this notion of coverage can be then expressed as a task, and the advantage of being expressed as in that notion is that then, irrespective of what the slope is, whether it is stuff that you've seen before, or whether it's a surface that it's not seen earlier, or if it's a curved surface, this notion of wiping gets transferred. So in this case, this is a notion that this is a slope that is not seen, so it's adapted motion to ensure that the concept of wiping gets implemented, not mimicking the movements, for example. Okay, and finally, I would say that one of the things that we've applied this is in the concept of snake robots. So this is in collaboration with a company called OC Robotics, and we've worked on, so the planning in these kind of robots require that we work in topology space. You need to work in, because the traditional way of planning with metrics don't really work. So in this case, here's an example of a snake robot with an actuator pack, and going in confined areas. So here's examples of robots that work in sort of nuclear energy plants, confined spaces, doing operations in really sort of narrow areas. And for this, the planning in this requires that we go away from sort of traditional methods of planning and work with concepts like rights, interaction mesh, things which define motion in terms of relational properties rather than absolute metrics. Okay, so I just want to finish off by showing you some of the things that we've been taking this work in the context of EMG sensors and prosthetics. So one of the things that we've done in relation with working with EMG sensors and prosthetics is, this is again in collaboration with DLR, is getting sensors, persons' biosignals to control a robot arm. So in this case, you can see a very expensive way of creating an omelette is to get a robot to mimic human hand from the EMG signals, decode the biosignals to actually control, in this case, this biosensors, the fingers of the robot. So I'm going to show you next a quick demo, and while I set up, I'll show you this video of work that we've been doing with prostheses with a company called Fast Bionics based in Livingston. And let me show you this video. This works.
A major goal in prosthetics is to create artificial limbs that both act and feel like real limbs. Researchers here at the University of Edinburgh, alongside the Scotland-based company Touch Bionics, developers of the award-winning IO, the world's first commercially available bionic hand. By amplifying signals from muscles under an amputee's stomach, the robot instructed to open and close its mouth in a variety of different types of growth. A major goal in prosthetics is to create artificial limbs that both act and feel like real limbs. Researchers here at the University of Edinburgh are working alongside the Scotland-based company Touch Bionics, developers of the award-winning IO, the world's first commercially available bionic hand. By amplifying signals from muscles in an amputee's stomach, the robotic hand can be instructed to open and close the mouth in a variety of different types of growth. The fingers automatically stop when they form a firm and steady grip on the object, allowing the patient much more dexterity than ever before in a prosthetic device. One thing we often take for granted is our sense of touch. Yet without it, we would find everyday tasks a significant challenge. There are thousands of nerve in every one of our fingertips. We grip objects sufficiently so as they do not slip from our grasp, but not too hard that they might break. However, amputees do not have this luxury, making what would seem a simple task rather difficult. The key idea behind our research is that for successful use of a robotic hand, patients require not only the ability to control the hand, but also continuous sensory feedback. At the University of Edinburgh, we're examining ways of interfacing this sensory feedback with the nervous system. By passing small electric currents into nerves in the upper arm, or by creating patterns of vibration on the skin, the amputee can gain a brand new sense of touch. We fit patients with the eye level and add sensors to detect forces on the fingertips. The signals from these sensors are processed and then communicated to the patient by electrical or vibratory stimulation, and this feedback can be used to coordinate and control the robotic hand without relying on constant attention, allowing the patient to get on with their daily lives. We are presently running experiments to understand exactly how the brain is able to learn to use the artificial sense of touch we have created, and how, with practice, we stop thinking about it, and it all becomes quite natural.
Okay, so I'll just quickly show you demo this thing working. Okay. So if you guys want to come in, you're welcome to. So there's a little crowd. That's why I'm waiting for Andy's talk. So you can actually. So I've now worn an EMG sensor, and I'm actually able to control the hands. And lifting, so this is again using the best of so the human contextual decision making along with the real-time processing capabilities in a robot hand. So would anybody like to try it on? I probably need one more person. Just to think. Okay, so what I'm going to try and do is to get you to control the thing, and you can swap it around later on. Okay, so I'm going to first get you to wear it. It's rather heavy, and I need you to show me I probably need to take your jacket off because I need to get your muscle signals out from. Okay, so you can support it for the moment. Yeah, go ahead. Yeah, good. Okay, so let's. Yeah, please. Okay, so this obviously the sensor is tuned to my biosignal, so we'll see if it works or not. But let's see. Okay, so what I want you to try and do now is we're going to turn around so the audience can. Okay, good. And so just move your wrist left and right. Okay, once it's set on. Okay, we'll try it. Yeah, just the wrist. The arms, the fingers don't matter. So just go one direction and the other. Perfect. Okay. So. Other way. It's a bit counterintuitive. Yeah. Excellent. Open it. Excellent. Well done. Okay. Thank you.
Let's see. Let's pick it up.
Okay. Okay. Collaborative robotics here. Go. Excellent. That's good. So, do you want to have a go in terms of wearing it? Okay, I knew that you were expecting that. so let me do. So what I can do is to give you a slightly cooler version 2 of the hand. Okay. So just want to show you that it's easy to sort of take it off. And so this is version 2. Slightly more funky. Okay, but it's version 2, so it's no guarantee it's going to work. It might explode. Okay. So this way. Yeah. You want to try and. Okay, and okay, let's give it a shot. Okay, so face this way, and we'll turn it on. Okay, we'll try. No, just the wrist, no? Okay. Wait. Okay. Okay, again. Just the wrist. Good.
Also creating this.
Yeah. Yeah. Good. Excellent. Great. Excellent. It's pretty heavy, yeah? That's how your hand, how much your hand actually weighs. So good. So you can see people you quickly learn how to control their arms. So, well done. Good. Excellent. Great. Okay, so I'm really out of time, so I'm just going to quickly summarize and finish. So, we've looked at how robotics, robotics and machine learning together can be an exciting science, because we've got lots of fundamental interesting questions that robotics throws up, and it requires obviously expertise from multiple disciplines. We're in an exciting era of growth in robotics, and most importantly, I think we're now seeing many sort of real-world challenges, and I'll show you an example in the next slide of the DARPA robotics challenge that we've been involved in, and it's really starting to make a real change. And one of the key drivers for that is because we've applied machine learning techniques, and we've harnessed the advances in these machine learning techniques and applied it to the domain of adaptive real-time control. So, so one of the challenges we've been involved in is the DARPA robotics challenge. This is a challenge about getting robots to actually traverse, humanoid robots to actually traverse very complex terrain, do tasks, autonomously do tasks like cutting sort of through holes, turning walls, climbing a ladder, kind of stuff. So, so let me see if I can find that video here. So the latest that you'll see, let's see if you can find that. Yeah. Okay, so this is the latest from our collaborators in Florida. And that is the state of the art of walking on an Atlas robot that you'll see. So this is the autonomous, so again, this is just a tether. It's not about holding it, but you can see it's autonomously sensing. This is a full body, full size, it's a 160 kilo robot. It's kind of close to a killer robot with a built-in sort of actuators, so built-in power generation capacity. So yeah, so that's the kind of stuff that we're going towards, and I want to sort of stop here by acknowledging the people who funded all our work, as well as all the fancy toys, and just a little advertisement for PhD students or possible potential PhD students. We're running a new, we've just launched the new Edinburgh Centre for Excellence in Robotics and Autonomous Systems. Exciting times ahead for that kind of work, and we've got many interesting platforms that we work with. And yeah, I think maybe for those of you who have not seen this video, it'll be fun. I want to stop by showing you this little quadrotor magic. Okay. Hopefully it shows up. Have you seen this video? So this is from a collaborator of mine, also called Vijayakumar, at the University of Pennsylvania. And you'll soon notice the theme. Thank you very much.